2, we studied of N, L, and M quantum number. Am I audible? There is some sound coming. Is it people joining or is it something else?
You're audible. No problem.
Okay, because I don't see my face. It's just a
Yeah, it's
window.
okay. It's okay. Video is also.
So chat also I will not.
Video is also.
Okay, good. So in the bachelor's level and the +2 level, you have studied the N, L, and M, which is the principal quantum number, the orbital angular momentum quantum number, or the azimuthal quantum number, and the magnetic quantum number. In the context of energies of hydrogen atom, right? And we also studied their interdependence. Here, I will like to focus on the dependence of L and M, the orbital angular momentum quantum number and the magnetic quantum number, L and M. You know that any particular L, so you see that if you have, when L is equal to 1, that is p orbital, there are 2L plus 1 ML values, or the magnetic quantum number values, ML plus 1. What are those ML plus 1 values? These are -1, 0, and 1. So if your L is 1, when you have 2 p orbitals, your L is 1. Then there are 3 2L plus 1. So 2 plus 1, 3 ML values. And what are those? Those are -1, 0, and 1, which is -L to +L with an interval of 1. Right? So this is the dependence of L and ML value. L and ML value. Now we call this 12 plus 1 degeneracies of L. Okay, so this 3 is the degeneracy of your L value. Degeneracy meaning having states which are same in energy. So there are 12 plus 1 ML values which are degenerate. So this we call as Px and Py and Pz, though not exactly corresponding to ML -1, 0, and 1, but still we know that there is a Px, Py, and Pz p orbitals. So in each atom, all 3 p orbitals have the same energy. You remember that. But when you put this in a magnetic field or even an electric field, this degeneracy, these states having the same energy levels, they are lifted. That means their energy now, if you have a electron in your p orbitals, their energies, depending on your ML values, will be different. Okay, so these 3 p orbitals will not have the same energy. They will have different energy if you apply a non-spherical magnetic field or an electric field. If you have a spherical magnetic field, they will all be enhanced by certain value, but not splitting. But if you have a non-spherical magnetic field or a electric field, you will get a splitting in energies, or you will have different energies. Now we come to spin. Now we've talked about N, L, and M, right? The principal, azimuthal, and the magnetic quantity. I told you L is a angular momentum, orbital angular momentum. Here the orbital angular momentum quantum number. Now when it comes to spin is also like an angular momentum. It's like an angular momentum. It has all properties of your L, the orbital angular momentum. There are some properties which are different, and the most obvious property is that the S spin quantum number can take also half integers. Okay, the L value, the orbital angular momentum quantum number, can only take integer values like 0, 1, 2, 3, etc. But your spin quantum number can take 0, 1, 2, etc. That is the integer values, but also it can take half, 3 by 2, 5 by 2, and things like that. Okay, so it can take these two. So this is the one of the differences. There are other differences also, but then major properties are very similar to the orbital angular momentum. The spin quantum number or spin angular momentum will have similar properties as the orbital angular momentum. So like ML values, which are 2L plus 1 degenerate L values, there are MS values, right? MS values, which are basically 2S plus 1 degenerate S values, right? So MS values would be 2S plus 1 degenerate S values. So if you have S is equal to half, that is the spin quantum number is half, then how many, how many MS values? So S is equal to half, then how many MS value? There is, it goes from -S to +S, or 2s plus 1, that is 2 into half plus 1, which is 2. So this is s is equal to half minus s2 plus half. So minus half plus half. So there are only two values, right? There are only two half values, plus half and minus half. And then this is the fundamental relation between S and MS. So what? But what is a physical picture? We can clearly see how mathematically they are related, S and MS value. But what is the actual physical picture? Now, this is a standard pictures that you can see in many of the books about angular momentum. It's not only for spin angular momentum, for many other angular momentums. Now, I'll try to explain why these are. Since obviously we cannot see the spins or electrons and things like that, so we have to use a vector picture. Okay, and we know that angular momentum, we said that the angular momentum and spin angular momentum are angular momentum. So what is an angular momentum? Angular momentum is a vector. So it has a magnitude and it has a direction. Okay, so it has a magnitude and it has a direction. Now the question, especially in quantum mechanics, is to whether we will be able to determine all of its what direction this is and what is the magnitude of the quantity. Okay, so unfortunately, because of uncertainty principle, we cannot. There is a lot of uncertainty in its direction properties, but obviously we can determine its magnitude. So we can always represent the spin angular momentum or even the orbital angular momentum as vectors. Now vectors obviously has a direction and a magnitude. So you have seen that this is your S spin, which can be S is equal to half or 1 or whatever. Let's assume that this is we are talking about S is equal to half spin. Okay, now this vector has a magnitude. And what is that magnitude? That will be root of S into S plus 1. This is like the same magnitude that is in the orbital angular momentum. You probably H cross. Root of S into S plus 1 H cross. For a spin half, that will be root 3 by 2 H cross. Okay, root 3 by 2 H cross. Now, what are these MS values? So we are talking about the relation between S and MS, right? So what are these MS values? The MS value is the projection of this S in the Z direction. The projection of this vector in the Z direction. Okay, or component of this vector in the Z direction. That is your MS values. Okay, so and what is the value of that? That is given by MS H cross. So this would be your MS H cross, and that will be this length. This is your projection, right? So that will be that length, MS H cross. Right. So this is your length. So now if your spin is S is equal to half, then your MS, as I told you, it is equal to plus or half. So you can have half H cross or minus half H cross. Half H cross or minus half H cross. Okay, now this is not, we have not introduced any magnetic field or anything. Okay, so this is the two component that we have. Now you see this this cone here, right? Now why is it represented as a cone? Because of the problem that we cannot simultaneously determine the y, the sy and sz. We only know what is your sz. Sz is half H cross or minus half H cross, but we will not know Sx or Sx or Sy, the component along the y or x direction. Okay, so we do not have an information, or we do not have the information on of the spin in the x and y component. So we can only know the magnitude of the vector and the component along the z axis, which is the MS H cross. So this is the relation. This is the relation. And why do we have this in a cone? Because since we do not know, this vector can be anywhere in this cone and still satisfy these two relations. That is root 3 over 2 H cross and half H cross or minus half H. If it is minus half H cross, this is the cone it will trace. Okay, this is the cone it will trace. If it is plus half H cross, this is the cone it will trace. The top one will be the cone it will trace. If it is plus half H cross, this is the cone it will trace. If it is minus half H cross, this is the cone that it is going to trace. Okay, so that is what we have. Now, if you have spin is S is equal to 1, then obviously you get this cone also, which is basically a circle along the SXY plane. Okay. Now, now we put. Now, how does can't go right? Now, how is this angular momentum, the spin angular momentum, related to magnetic moment? Because only when you have a magnetic moment can it interact with a magnetic field. Okay, so you have to any substance or anything that will have to interact with the magnetic field, it should have a magnetic moment. It should have an intrinsic magnetic moment. Now, how is that related? A magnetic moment is directly proportional to your spin quantum number. Spin quantity, your half, right? That is directly proportional to this, and the directionality, the proportionality constant is your gyromagnetic ratio. Just like Bharat had said, it's the gyromagnetic ratio, and that specifically is determined by the nucleus you're looking at. Okay, hydrogen has a particular gyromagnetic ratio, carbon has a different gyromagnetic ratio. Similarly, fluorine will have a different gyromagnetic ratio. Okay, and so that was the magnetic moment. This is the magnetic moment that will interact with the magnetic field. Okay, that will interact with the magnetic field and will tell you whether the energy that is associated, whether this direction is having a lower energy or this direction is having a higher energy. Okay, that magnetic moment is the magnetic moment will tell you exactly. So it depends also on what is the charge, not the charge. What is the sign of gyromagnetic ratio? Okay, if gyromagnetic ratio can be either positive and negative. For example, proton has positive gyromagnetic ratio, while 15N, for example, has a negative gyromagnetic ratio. So your plus half, which seems to be always have a lower energy because they align with it. It is true for protons, but when it comes to nitrogen, that is wrong. It's the minus half which has a lower energy than plus half. Okay. So what is this energy we are talking about? The energy or the splitting is what is observed by Siemens, and so this effect is called the Siemens effect. And what is this energy? Energy is a dot product minus mu dot B, and I just told you what mu was. Mu is gamma S. So you can calculate the energies, and it will be equal to E is equal to minus gamma MZ or MS H cross B0. MS H cross B0. So for a spin, for S is equal to half, there will be two energy levels. Like here, you have two energy, plus half and minus half. And assuming your gamma is positive, okay, your plus half will have lower energy because your negative sign is here, and minus half will make this positive, so therefore it has a higher energy. Okay, so this is what the energy is, and you can calculate the difference in energy, which is gamma H cross B0. And the frequency, because this is energy, you can convert that into frequency, and frequency is going to be gamma B0. So your frequency depends on your magnetic field. Okay, it depends on your magnetic field, it depends on your gyromagnetic ratio. So different nuclei or different type of nuclei, different elements in your periodic table will have different resonant frequencies. Okay, and also the frequency depends on the magnetic field. So magnetic field has a very important dependence on the frequency. For example, just look at 1.41 Tesla. The energy gap is this much. Okay, the energy gap is only this much. But as you increase in Tesla, let's say this is at 7.4 Tesla, the energy gap is larger. You go further, like 11.74, the energy gap would be much bigger. Okay, this has two important things. One is that the large number of molecules, especially if you are in a lower magnetic field, the population difference between the higher and the lower state will not be so much. And you have seen in Bharat's lecture that if the differences are very small, the sensitivity is going to decrease, right? So you have to, that is why we go always to a higher magnetic field in order to get better NMR spectrum. Okay, so higher magnetic field would help in increasing the population difference between the two states. different states of your spins. Now, in all these things, I mean, all this energy gap, the frequency that you have calculated, that comes in the radio frequency region. Okay, radio frequency region. Okay, radio frequency has the lowest energy, and you know that if any one of you actually gone into an MRI machine, like Bharat said, that MRI is nothing. It's Nmr, but if you have gone into an MRI machine, you have to stay longer. You have to stay longer to acquire, because the sensitivity of Nmr is small. You are working in very small fields. No, you are actually working in this region. Actually, in this region, less than 1.4122 Tesla. Okay, so your energy gap is really small. You have to acquire a large number of scans in order to get a good spectrum. Okay, and so lots of acquisition is being done, and you have to stay. You are the sample. You have to stay inside the magnet for quite a long time, maybe 40-50 minutes. While on the other hand, if you are in an X-ray machine, or you go to an X-ray or a CT scan, it's done very quickly, like that it goes, and you don't stay for 45 minutes. If you have stay for 45 minutes, probably you will end up, if you are lucky, you will be Spider-Man or somebody, or otherwise you get cancer and other terrible diseases. So, but NMR has no, or MRI has no problem, because the energies that we are dealing with is really, really small. Okay. Oh, so this is the resonance. You have a spin which is up, the MS being half, and then for a positive gamma, and then you apply radio frequency, you flip the spin, and the absorption is what we see. So NMR is an absorptive spectroscopy. Okay, and that is what we. But the problem is that how we actually acquire it. Acquiring was not that straightforward. Not like any other instrument where you just scan the frequency and then you get a peak. No, you do UV or IR. It's pretty straightforward. Okay, you change the frequency, there is an absorption, and you read out the absorption. Use a Beer-Lambert's law and things like that. That is not possible, because the energy gap is so small. Because radio frequency is the frequency range we are determining the absorption in. Okay, and in such energy gap being small, meaning the population differences are small. And if the population differences are small, there is far less population in the lower state to get excited, because I told you it's an absorption spectroscopy. So the far less population in the ground state to get excited to the excited state. Okay, so it was not until 1947 that there was an efficient method of determining the, especially nuclear spin, not electron spin, but nuclear spin. Okay, so we have seen this picture. I think Bharat also had mentioned. You apply. Keep losing it. Okay, good. Yeah, I think this slide is killing me. Anyway, you apply a constant B0 field. B0 field is an applied external magnetic field. You have to have a constant magnetic field. Only then we have a degeneracy in the MS values. Only then you will get us difference in energy. Unless you don't put this molecules or nuclei in a magnetic field, you don't get Siemens effect, and therefore there is no splitting in energy, and therefore there is no NMR. And it also will work only when you have a non-zero spin quantum number. Okay, if you have a spin quantum number 0, there is no NMR. Thankfully, every isotope in, I mean, there is even the natural isotope may not be a non-zero one, but there are other isotopes of the elements which will be non-zero, and therefore you can do NMR in most of the elements that you see in the periodic table. So you have a magnetic. Okay, I think I cannot go into that. Okay, My iPad is low. Anyway, so what I wanted to say is that we are not looking at a single spin. We are looking at multiple spins. So in your cone picture of your spins, it's not like one single spin is there. There will be multiple spins in your whole molecule, because we are taking 1 mole of, let's say we are taking 1 mole of samples, then you have 6 into 10 raised to 23 molecules of your compound, and depending on how many active NMR nuclei are there, then you will have so many cones. So they have a large number of cones. Many of them will be pointed having lower energy. Some of them will be having higher energy, and you will have a multiple cone picture. Now, if you put all together, together, these vectors that you see here, are individual cones. So not this vector, but these vectors. Okay, and you see these vectors in this directions also. Now, what happens here? Because we use a random phase assumption, that is, the xy component of these vectors, this vector, for example, xy component of this vector will cancel out the xy component of this vector, and only the z component gets added up. Similarly, in the higher energy state, which is in the negative z axis, because your magnetic field is along the z axis, the number of vectors will be small, because the number of nuclei having a high energy will be slightly less. Therefore, this magnetic moment, which is also an addition of all the vectors in this minus z axis, this magnetic moment will be smaller than this magnetic moment. Why? Because the number of vectors in this direction is higher. In this direction is higher than this direction. So you have a bigger field, bigger magnetic moment in this direction compared to this direction. And you take the difference. So you will have a net magnetic moment. You have a net magnetic moment, which we call the M0, aligned with the magnetic field. Okay. We can do the maths for this, and it turns out this magnetic moment, this M0, is proportional to, was equal to the N, the total number of spins, the gyromagnetic ratio, the magnetic field, inversely proportional to your temperature. So M0 is directly proportional to a concentration. So the higher the concentration, the bigger the M0 is. The larger the magnetic field, your bigger your M0 is. Lower the temperature, your M0 is also going to be big. Okay, so this is how you want to. So now what we are going to discuss is how we can observe this M0. Okay, this is now getting into the classical picture of NMR. Okay, so what we have to do, we are applying a magnetic field, a strong magnetic field, strong constant magnetic field in this direction. Let's say this is the direction, right? This is the z axis. So this is your z axis. Okay, this is your z axis. Then this is a coil. This is a coil that is wound like that, right? And that is producing this B0 magnetic field. That magnetic field be B0. Now you have another coil that is perpendicular to this B0 field. Okay, this coil is perpendicular. This coil is perpendicular to your B0 field. Okay, and this is called the RF coil, radio frequency coil. And the magnetic field generated by that is the B1 field. So what we are in an NMR instrumentation, this is what we are doing. We apply a magnetic field. We apply a constant magnetic field B0, and then across it, perpendicular to it, we apply another magnetic field, which is the radio frequency. Okay, because the radio frequency has a magnetic field, right? Because it's an electromagnetic radiation, and that magnetic field is B1. But this is now going to be perpendicular to your applied. This is going to be perpendicular to your B0 field. So B0 field is in one direction, and perpendicular to that, either Y or X, you have to apply the B1 radio frequency field. So in this way, we should be able to get this magnetic moment, which is in this direction, which is in this direction, to move away from the B0 field. Okay. Now in this picture, you see that B0 field is this direction. The magnetic moment will also be in this direction. You will not be able to measure this because you are sitting, this magnetic moment is sitting on a huge magnetic field. Now you have to get this out. You have to hold that M0 and then push it out of your B0 field. Now how do we do that? We can do that. Bharat had shown that equation M cross B, right? And that is why you have to apply something that is proportional. You have to have a torque that makes it come out of your B0 field. Okay, then we should be able to detect this M0. Okay, so in order to do that, we have to apply, because that is why you get a sin theta dependence. So you have to, you have to apply a B0 field, which is B1 field, which is perpendicular to your B0 field. Now, how do we do this? We just don't apply a radio frequency like this. Okay, we apply a short burst of radiation, a pulse. Okay, now what is a pulse? A pulse is a short burst of radiation, and you've seen what is a pi/2 pulses, right? Now, how do we generate this? Well, you go through a gating mechanism where you have an amplitude of this pulse 0 at some point, and then suddenly you open the gate, and for a few microseconds you open the gate and then close it off. Okay, and this small durations should be sufficient. The magnetic moment will, if it is a pi/2 pulse, then the magnetic moment goes from the z-axis to either x or y after the application of the pulse. So after the application of the pulse, the magnetic moment goes from the z-axis to either be in the x or y, depending on which direction you're applying, either along the x or y direction of your pulse. Okay, so this is a short burst of radiation that is sufficient to excite most of your resonances in your signal. So in the old days, we had what is called continuous wave. A continuous wave of is a guy who likes playing piano one key at a time. Ting, 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 it goes. But then a Fourier transform. Now what happens in a continuous wave is, I mean, normally what they did was to actually fix the frequency and sweep the field. Okay, fix the frequency and sweep it. So as it touches the correct frequency, okay, of a particular spin, you get an absorption. Then it goes. But you should remember that the intensity will be very small, because obviously of the insensitive nature of NMR. Now then you have to come back and do the measurement again. But it will take a whole lot of time before you come back, because you have to wait for the magnetization to relax. Then you do the sweep again. Okay, you have to go very slowly, and you have to do it really, really slow in order to hit every resonance correctly. Now that Fourier transform NMR helps to alleviate, or pulsed Fourier transform NMR helps to alleviate this, because when you are applying a pulse, this is a step function in the frequency domain, in the time domain. But if you do a Fourier transform of a step function, what you see is a sinc function. Sinc function would mean that there is a large number of frequencies that is getting excited. And it is one shot. It's like one shot, and you excite every resonances in your signal. Okay, you have seen in the previous lecture that there are multiple resonances depending on the different chemically equivalent, different environment, right? Just looking at the carbon or protons. So you will have multiple peaks. So this short pulse would be able to excite most of, so for example, if you apply a pulse on the hydrogen atom or proton NMR, you will only excite proton NMR. You will not be able to excite carbon-13, because the frequency of carbon and proton are very different. Okay, so you have to excite. It's just like in your radio. A radio, you wanted to tune into 93.5 FM. Now, you hope not to see 94.7. You only wanted to hear 93.7. So you basically go there and tune to 93.7 and hear the FM. But if you want to listen to 94.7, you have to change your knob or press a button to get to 94.7 frequency in order to hear the 94.7 FM radio. Here, if you want to really see only proton, then you have to tune your frequency, or your applying frequency has to be on the hydrogen resonances, which is, if you are taking 11.74 Tesla, that is around 500 megahertz. Okay. But then if you want to look at carbon-13, you have to tune the frequency to your carbon-13 resonance, not at 500 megahertz. At 500 megahertz, pulsing at 500 megahertz, you cannot hope to determine or see your carbon-13 NMR, because that is very far. Your gyromagnetic ratio of carbon-13 is 1/4 of your proton. Okay. Therefore, the frequency omega 0, as I mentioned, that is gamma B0, right? And gamma B0, the gyromagnetic ratio is 1/4. So 500 divided by 4, that is around 120 hertz, 120 megahertz. So you have to tune your or you have to sit on a resonance or sit on a frequency that is 120 megahertz in order to see carbon-13 NMR. Similarly for nitrogen 15. Nitrogen 15 is 1 by the gyromagnetic ratio is 1/10 of proton. So for a 11.74 Tesla, that resonance frequency will come around 50 megahertz. So you have to go to 50 megahertz in order to see carbon 15 NMR. Okay, so rather than working on these cones, so this is you can see that this is a B0. You have applied a B1. There is a resultant field. That is because this is another one vector here, another vector. There is another vector. That is a resultant vector. So your spin. Previously, there was only B0 field. Before B1 was 0. B0 field. So your spins were revolving around in this direction. Okay. Now, when you apply a B1, that is a RF field, now there is a resultant field because of the B0 and B1. You have a resultant field BT, and the spins are going to revolve around the resultant field. Now, this is so many cones and so many revolutions. Rather, in order to picturize it, we go into something called a rotating frame. Okay, a rotating frame is very similar. That if you want to see, look at your fan in your room. I wanted to clean the fan when it is still working. Okay, clean the leaves of this fan when it's still rotating around, right? Revolving around, rotating around. So when it's switched on. So how do I do that? Now, if I just put my hand up, then it will, my hand will break. So what I can do is to get into a rotating frame, a turning table, which has the same frequency as my fan. Okay. Now, if I get into that table, a rotating, a table which has the same frequency of fan's blades rotation. Now, if I go into that frame and look at the fan, what will you think? What will you see? You see that the fan's blades will be stationary. Okay. With reference to your rotating frame, you see that the fan's leaves will be stationary. Now I can actually clean the fans. Okay. There is no problem. But don't look downstairs, because when you're down to a stationary frame, then you will fall down. So just get into a rotating frame and we'll be able to clean your fan or switch off the fan. So in NMR also, in order to represent it, we go into a rotating frame, and we can always then represent it as single vectors and move accordingly. If you apply a pulse, this is a small video, if I can play this. Yeah, if you apply a pulse in this direction, this magnetization, this red one was a magnetization, that will come. You apply a 90-degree pulse, that will drop onto this here, and then it will move around like this, and goes back to equilibrium position. Okay, equilibrium position. So you have two coils here, one along this, let's say this is the Y direction and this is the X direction. You have two coils, and this magnetic moment, when it is in the XY plane after the 90-degree pulse, will cut these two coils, creating a current. and that current is what we see here. So you see that this will be the coil that cuts here, so the red one, and this blue one would be the coil, the magnetic moment cutting this thing. So you got two coils, two currents, which is phase shifted by 90. Okay, this is what we call the free induction decay, which we then Fourier transform to get your signal. How do we do the Fourier transform? Well, basically we digitize this signal. I'm sorry, I'll have to get into. We digitize the signal. Okay, digitize the signal. That's like you convert from analog to digital converter. So pass through analog to digital converter when we actually speak and all, and our voices are being converted from a mechanical thing to a digital thing. Finally, it is being transmitted, and then you receive, and then you hear it by the reconversion from the digital to a mechanical oscillation. So here we go from a current which is then digitized and then fed into a computer, and what you get is something like this, which is the free induction decay. So you see, this is the time and this is amplitude, which we Fourier transform in order to get the frequency. I will shift through this longitudinal and transverse relaxation. Transverse relaxation, I told you, is for solution state at least. This is much shorter than the T1. Longitudinal relaxation, and this basically determines the line width. You have seen in the cartoon or in the video that the magnetic moment doesn't stay in the XY plane after the 90-degree pulse. It goes back. That relaxation, there are two types of relaxation: transverse relaxation and longitudinal relaxation. Longitudinal relaxation is getting back to equilibrium. Transverse relaxation is how fast it gets spread in the XY plane. This is like a bunch of sticks that you take, and the pulse basically ties these sticks together. And when it is put to the XY plane, you stop the pulse. Okay, you stop the pulse. That is when the pi/2 pulse is done. Okay, that means the tie that holds these sticks together is released. Now what happens to these sticks? They just spread out, right? And that is what basically happens here. So it is decoherence. Your coherence, and then it becomes decoherence after the pulse is over. Okay, and how fast it does it is given by the is given by the T2 relaxation rate or the transverse relaxation. So there are two signals I told you, the cosine part and the sine part, which is phase shifted. Cosine and sine are phase shifted by 90 degree. You are then allowed to combine them together in order to create a complex. Okay, you add, so you take the cosine part, you take the sine part, you multiply it by I, and then feed to a computer algorithm which will do the Fourier transform. Okay, and the Fourier transform, I don't want to go into the mathematics. You will get a Laurentian signal, absorption signal. You have an imaginary part, which again Bharat has discussed. Now we come to the NMR. This one, in solution NMR, we start with a NMR tubes like this, right? And the volume we fill it up to is 55 centimeter or around 500 microliters. Okay, so this is the lower part of the tube. This is the top part of the tube. Okay, and we adjust it using this apparatus here, such that there are markings here, which we make it very sure that they are in the middle of the sample, around 4 or 5 centimeter. Okay, so which makes sure that your sample is right in the middle of your magnetic field. So this is a standard NMR room that you will see. There are multiple things that you can see here. This is actually from Princeton University. I don't have a picture of our NMR. There is a spectrometer where we actually have all the equipments, that is, I mean, all the part that is required for the pulsing and receiving of signal. This is the magnet, a huge magnet. This is a preamplifier. Okay, it goes from, there is also, of course, computer that sits and controls the spectrometer, and the person who should be able to control the spectrometer. The signals, everything is generated here. Signals meaning the radio frequencies, everything is synthesized here, which is then fed to the this region, which then goes into the probe. Okay, probe here. This part is called a cryo unit, which is useful in cooling down your probe such that your noise becomes very small, because your the noise that that Bharat was mentioning about signal noise, the noise he mentioned was mainly from the electronic noise. You can reduce this electronic noise by cooling to a very low temperature. When you cool it to a very low temperature, that is around 16 degrees, 16 Kelvin or something like that, you will see a high reduction in noise. Therefore, your signal to noise will go up. Okay. So this is a small video about what the NMR. It's playing. So this is Bruker from Bruker company. There are two companies, Bruker and this is the probe. Okay, you see the sample. This is a spinner. Normally we don't spin the sample if it's a proteins and everything. For small molecule, some level of spinning is good to get a more sharper peaks, but then it will introduce some spinning sidebands. This is the magnetic coil, which is a B0, which produces the B0 field. This spinner goes in because using a cushioned air and sits right in middle of the magnetic field. Okay, and this is a probe. Okay, the probe is a place where you apply the radio frequency. Remember these probes are sitting, or these samples are sitting in the room temperature, but the magnetic field or the magnetic coil is not sitting in the room temperature. Your RF coil is also sitting in the room temperature or the temperature that you desire, but not at very low temperature. Yeah. Now, why I say about low temperature is this: you need a very high high magnetic field homogeneity in order to do NMR. Why is that? Because your NMR, as you know, depends on your omega depends on gamma B0. Now, at different point of your sample, if your sample is like this, okay, and this is the sample. At different points of your sample, if your B0 field, the field is different, your omega will be different, right? So the same sample, the same spins will have different frequency, will show different frequency if your B0 field is not uniform. If the B0 field is uniform, you will get only single spin, single signal. But if your B0 field is different, that means if the field experienced at the top of the sample and the field experienced at the bottom of the sample are different, then we will have different frequencies, right? So that is a problem. So in order to have a highly homogeneous magnetic field, that's the whole point. That is a major cost in making a magnet. It has to be wound to a very specific way. Only then these coils that I'm talking about, these superconducting coils, has to be wound in a very specific way. Only then you can create such highly homogeneous magnetic field. Okay, and that is where the cost of the NMR is. So, for example, if you are talking about a 600 or 500 megahertz, that is around 4.5 crores. If you're talking about 700, that will be close to 9 crores. And there are magnets up to 1.2 gigahertz, that is 1200 megahertz. Okay, these are all frequencies of protons. Okay, that means we in NMR we say it in frequencies of protons, resonance frequencies of proton. Now, this superconducting magnet obviously has to be wound in a very specific way, and this is superconducting at very low temperature. You don't have room temperature superconductors, so it has to be maintained at a very low temperatures. That is at 4 Kelvin or even 2 Kelvins. So that requires that you have liquid helium in your system. So these coils that you see, this is only half part of the coil. You see that has to be immersed in liquid helium. Okay, so it is very important that the superconducting magnets are immersed in liquid helium. Then, because you don't want it to you don't want it a direct temperature gradient from the outside, room temperature to the liquid helium, what we have is a nitrogen blanket on top of the liquid helium. So you have a nitrogen blanket, liquid nitrogen blanket on top of the liquid helium flask. So there are multiple flasks here, right? The inner flask has liquid helium, and the outer flask has nitrogen, liquid nitrogen, and the outside everything it's covered in vacuum and everything. You see the bore that goes here. Okay, so this is like a tube. That tube, that goes from the top to bottom. Okay, this is at room temperature. So this whole flask is covering this bore here. So there is a bore that goes from top to bottom. Your probe head, which supplies your radio frequency, the radio frequency coil is sitting on this probe head. Okay, that goes from the bottom. And your sample comes from the top and then sits right in middle of this magnetic field here. Okay, so here is again another picture. You see the coil. This is a superconducting coil. So this is a 2D picture, and this is your probe where you have the radio frequency. This is your sample. This is your sample with the spinner that is sitting on the middle of this magnetic field, as well as your radio frequency coil. Okay, this blue thing is helium, liquid helium, and this red one is a liquid nitrogen. Okay, so you can see that there is different filling time. Okay, liquid helium are normally filled. So liquid helium, the temperature is at 4 Kelvin, 2 Kelvin, 2 Kelvin, right? And every 6 months or so, for us, especially in 500 megahertz magnet, we have to refill this liquid helium. If the temperature, if we don't maintain this temperature for 2 Kelvin, then this will warm up, creating a cascading events, which will then quench everything. Whatever remaining liquid helium is there, it will burn off. So we have to always maintain the liquid helium to a certain level. Similarly, you have to this liquid nitrogen blanket should also be filled every week. Okay, so around 50 to 60 liters of liquid nitrogen is required every week in order to maintain the nitrogen level, so that the gradient between outside temperature and inside temperature is less. That is why you have a liquid nitrogen temperature, a blanket of liquid nitrogen. This will evaporate much faster. Liquid nitrogen is cheaper than liquid helium. Liquid helium is a noble gas, right? So, I mean, helium is a noble gas, right? And it's very rare. And nitrogen, on the other hand, is 78% of the atmosphere is nitrogen, so you can liquefy that. So that nitrogen is cheaper, generally cheaper. So we have to fill every week. However, okay. No, I don't. Right. So for any magnet which is less than 10 Tesla, the wires that makes the superconducting magnets are made up of niobium titanium alloy. But anything above 10 Tesla, it is made up of niobium tin alloy. And again, as I mentioned, it has to be wound in a very specific way in order to get such high homogeneous magnetic field. If you really want to have higher field, there is no problem. There are magnets which can go up to 100 Tesla, 200 Tesla and all. But to get to a very homogeneous magnetic field, create and sustain that homogeneous magnetic field is rather very difficult. So the maximum that we have reached so far is around, I think, 23 Tesla, I don't know, 23 Tesla. We are nowhere near the 100 Tesla. So this is actual NMR rather than any cartoon or things like that. And you can see that this probe, this thing here, this is the tube, or this is the tube that goes from top to bottom. And you can see all those inner flask. The inner flask would be the liquid helium reservoir. The outer flask would be the liquid nitrogen reservoir. And in between each of them, there is a vacuum layer that separates them. Now, when in NMR, when it comes to NMR, there is important, again, I told you the homogeneity of your magnetic field, and for that we require what we call a good shimming. A good shimming is that we make sure that every part of your sample has the same magnetic field. What we do in such a situation is we apply current into the probe such that we compensate for any change, even how much you do the magnetic B0 field to be very homogeneous, but still they will not be sufficiently good to have a very high homogeneous magnetic field. So what we do then is to supply currents such that we compensate for the change in the or deviation from the B0 field, and we compensate by supplying a current which is opposite in direction, such that the field experience is the same throughout the sample. This is called a shimming. We can do that automatically. This is on the RF field, not on the B0 field. Okay, this is on the RF field. The RF should also see the same field across the sample. All right. So now we come to the signal generation and everything. As I mentioned, different frequencies will have different channels. Just like you have a FM. It's basically, this is a big radio, a huge radio, costs a ton of money, but that's a radio. Okay, so different frequencies will have to have a different synthesizer, different not a synthesizer, but different amplifier, different coils and stuff like that. There can be a certain coils that can be tuned, just like remember the old days when we were listening to radios. We have to turn a knob, right? We have to turn a knob. What are we doing while turning a knob? We are basically trying to match the frequency of the incoming frequency with that of the coil antenna. Okay, so that this antenna can receive that signal. Okay, so it's basically an LC circuit, and we are tuning that stuff. So in every frequencies, every nuclei, let's say here, for example, you can see 13C nitrogen and proton amplifiers, right? And proton amplifiers. So you have a signal generation unit, which makes the signal, the pulse signal, okay, and that generates the frequency. It is then fed to amplifier, which will generate how much of strength this. So you can have a pulse like this. You can also have a pulse like this. Okay, this is the amplitude of the signal. The amplitude of the signal, amplitude of the pulse, is basically created by the amplifiers. Okay, it's the same amplifiers that we have, not the same amplifier, but the type of amplifiers that you have in your music system. There is an amplifier which amplifies your signal, right? So here, the signal generation unit, which creates a small pulse, it is fed into an amplifier, which gives you a sufficient amount of amplitude, which sits on amplitude. That will give you exactly what kind of pulse you want. You want a 90-degree pulse, you have to have a particular power. Okay, and that power is generated by these amplifiers. Then that amplifier is directly going, this is going into this preamplifier. Now when the pulse comes, this is one-way thing. It will pass through, it goes through different channels. You see this carbon-13, nitrogen, proton, deuterium, right? Carbon-13, nitrogen, proton, deuterium, right? And so there are different channels here. Now, why there are different channels? Because the frequencies for each of these channels and also the power required for each of these channels are different. Okay, so that is why there are different channels. Now, if you want to have a different frequencies, you have to closely follow which one. For example, if you have some nuclei which is resonating at let's say 40 megahertz. Okay, 40 megahertz. Then it's better to go through the 15N channel, because then that can actually, in a 11.74 Tesla magnet I'm talking about, then the 15N frequency is around 50 megahertz. So a 40 megahertz would mean that it is very close to a 15N megahertz channel. So you can possibly, it's not always the case, you can possibly see that nuclei with the 15N routing. Anyway, so you go to the preamplifier. Now, in a normal case, when you are applying a pulse, this preamplifier doesn't do anything. It just opens up and then it feeds to the probe. Now, for the probe is also have different knobs. So there are different. For carbon-13, there is a coil. There's a 15N. Usually, carbon-13 and 15N are the same coil. Proton will have a different coil, and deuterium will have a different coil. Okay, so there is carbon-13, proton, 15. I'm talking about the major three channels: carbon-13, 15N, proton, and deuterium. Deuterium is always required, especially in solution in MR, because we are looking at the shim based on the deuterium, and also we wanted to look at the stability of the magnet based on the deuterium signal. Okay, so let's say that you have a nitrogen 15 channel goes to a nitrogen 15, and then it is pulsed there. Now, once the pulse, this is once the pulsing has stopped, that means now we are in the receiving mode. The same signal comes to a preamplifier. This is where the preamplification happens. The signals are really weak. We are talking about a small magnetic moment, right? So these signals are really weak. By the time it reaches our spectrometer, the signals would have died down. That is why these preamplifiers are there to amplify the signal before it reaches the amplifiers, and then it enhances again before being fed to the computer. So this preamplifier basically amplifies the signal that comes out and amplifies it, feeds it to the spectrometer, which then amplifies it further and then feeds it back to the computer, where it is then processed. All right. So this is how normal NMR goes. So when we are starting with a NMR probe, we have this following components. You have a RF detector, digitizer, pulse program, RF source. There is an RF amplifier, which is then have a computer and a screen. There is also a gradient pulse program and a gradient amplifier that is there. This computer controls everything. The computer where you are sitting and controlling everything, that is controlling all this part. All this part, the gradient, the RF part, everything is in that what we call the spectrometer. This part, this is the probe, that small cylindrical thing that goes from the bottom. That is the probe. So your computer basically has pulse program, which generates the codes for the pulse program. You execute that pulse program. Okay, so there is an RF source. Okay, now it is digitized. Previously there is a shoe mantle and everything which generated the RF source. Now there is a digital clock for doing this. So it creates these frequencies. The pulse program basically tells you what is the amplitude, what is the power of the pulse, everything, which is then fed to the RF amplifier. Then that RF output of the RF amplifier goes directly to the probe. There is a preamplifier here, but then preamplifier doesn't do anything for this thing, which then goes to the probe for a particular channel. If carbon-13 has a particular frequency, you have to have exactly that frequency being generated here. That particular RF power being generated, it goes to that particular RF coil in the probe. RF coil in the probe. If you want to have nitrogen 15, you have to go through the nitrogen channel, not through the carbon-13 channel, which is the channel, meaning the coil that is tuned to carbon-13 will not detect nitrogen 15. So you have to tune your carbon-13 coil to a nitrogen 15 coil, or you have to have a different coil which is there in the probe, which will be tuned to nitrogen 15. So you have to go through that. So that is how it works. Then from the probe, after the pulsing is done, and when you are in the acquisition mode, the probe have this magnetic moment that comes to the XY plane. Then it cuts the coil, creates the current, and this current has to come back. It comes to the RF detector. That means before it comes to the RF detector, there is a preamplifier which preamplifies, comes to the RF detector. It's then digitized from analog to digitizer conversion, and that is then fed to the computer, which we then Fourier transform. Okay, the gradient pulse and gradient probe are is used primarily to well, these are very important for MRI, because that's where all I was talking about the what is that called, the uniformity of the magnetic field, but in MRI we basically destroy that uniformity by applying gradient, and this gradient pulse program and gradient amplifiers are really required in that particular probe. But in NMR also we require it, especially for reducing the by shortening the what is it called, shortening the phase cycling. We can use gradient pulse programs so that we don't have to have a number of phase cycles to reduce the signal, spurious signals from coming. Right. So this is you can see the blob of the probe here. So this is the probe, and you can see the blob of the probe. You can see 15N, carbon 13, and proton. So if you want to observe 15N, the signal, the preamplifier after the RF amp, that thing should go and attach itself to this 15N. If you want to see carbon 13, that should go to the carbon 13 here. If it wants to see proton NMR, then it has to go through this knob here. Okay, so that is how we have to. So these are like your FM channels. Different FM channels will have different frequencies, and therefore, if you want to observe different frequencies, you have to switch between the channels. Okay, some of them can be tuned. Here, these are very dedicated TXI probes, so these are dedicated channels. But then there are other probes which are tuned to multiple frequencies. That therefore we will be able to tune that particular coil to multiple frequencies. That basically means that there is a large capacitor in those coils, which we can tune to multiple frequencies. This tuning and matching that happens is what I have seen in all days. This is done by going under the probe and then using this tune and match to, as I mentioned, it is an LC circuit. What we are actually doing is tuning, just like when we were in the old days, we were tuning our radio to a particular channel. Here we are tuning our coils to a particular frequency, whether it is carbon 13, proton, or nitrogen 15, or phosphorus, fluorine. We are going to tune it to that frequency. Not all coils will be tuned to all frequencies. Okay, there is that is determined by the LC circuit, how much of capacitance, how much of that is present in that coil. So not all coils will be able to tune to different frequencies. There is a capacity for its tuning too. Okay, and normally we have 3 channels. I mean, normally in every probe, especially in the colleges and other small universities, you can have probes which are only 2 channel, double channel probes. Double channel probe meaning you can observe proton, and you can either observe a heteronuclear. It can be carbon 13, nitrogen, or any other X nuclei. We call it X nuclei. But even in that X nuclei, it's not always that you can observe every frequency. Okay, that basically is determined by the capacitance that is there in your probe. Right, so this is a preamplifier, and you see so many knobs. So these knobs, from this side, the knobs comes to the spectrometer. So from the amplifier, those wires come and attach here. From outside of this, from this side, there are similar knobs out there, and that is getting attached to the probe here. Okay, so this goes here, and from outside it goes to the probe. I am almost done. So this is the blob, and this is the last picture. So you have a pulse programmer, which is attached to a signal generation unit. Okay, signal generation unit is where we have this pulse programmer. Of course, is connected to a computer, which basically determines what this pulse programmer does. It is connected to the SU, signal generation unit, which is then connected to the amplifier, which gives you the power of these pulses. Pulses is pi/2 and 180-degree pulses and things. And timing, power, everything is determined by this SGU. And this is then connected to the HPPR, which is the preamplifier, which is then going to the probe, different channels of the probe. Okay, and the return also, it is the same thing, and in a different line, not in the same line, but in a different line. But then the same path is traced. Okay, thank you very much. If you have any questions, please let me know. I think I have taken some more time.
The session is open for discussion. Yes, I think there is one question in the chat box.
size of the molecule. Ghanshyam Pai asks, sir, does the size of the molecule affect its relaxation times? Yes, it does affect its relaxation times. There are the relaxation rate is a very complicated process. It has to do with dipolar relaxation. I mean, there are two types of main. For a normal spin half nuclear, there are two types of relaxation. Two mechanism by which molecules relax. This is the dipole-dipole effect, as well as chemical shift anisotropy. So in all of this, and this depends on the tumbling motion of the molecule. Okay, tumbling motion. If the molecule tumble very rapidly, that means the spins don't see each other. Spins that is interacting, they don't see each other. Okay, I told you transverse relaxation is if you put everything down, it spreads out, right? So that means the energy that it has gained is being dissipated to other spins also. Okay. Now, in order for the energy to dissipate, there has to be certain coupling involved, right? If they don't see each other very frequently, then there is no. So, meaning they are not in contact with each other very frequently. Then they have the same type of interaction very frequently. Then the coupling will be very weak. Okay, so when the molecule tumble very fast in solution, then they don't see each other. The spins don't see each other very frequently, and therefore the relaxation rate is low, or T2 would be high. But as the molecule becomes bigger and bigger, this tau c, this tumbling motion, becomes restricted. Tumbling motion becomes restricted, and therefore they will see each other more frequently, and therefore there is more chance that the spins give energy to the others. I mean, and therefore they'll relax faster. Can you explain how the shimming process is carried out? Sonik Bhatti asked, how exactly the shimming process is carried out? Well, we look at, normally there are multiple ways of doing this, but what is generally done is we look at the amplitude of the deuterium signal. Okay. Now, if shimming is good, then you will get a sharp signal. If the shimming is bad, what do I mean by shimming is bad? Is that different points of your sample has different magnetic field. So then that means there will be multiple signals that overlaps, and therefore there will be broadening in your signal. Because the area under the curve has to be same, it will reduce its amplitude. The signal drops in intensity. Okay, so looking at the amplitude of your deuterium signal, there is a different spectrometer, or in the same spectrometer, but then deuterium channel is like an independent spectrometer. So looking at the amplitude of the deuterium channel, we try to change the current that flows into this RF coils such that we compensate for this deviation from the B0 field. Okay, and what happens? B0 B1 field. What happens if when you do that? If it is getting better, that means the shimming is getting better, or now the field is getting homogeneous. Then the amplitude is going to rise because you are removing all the deviation from B0. So the amplitude is going to rise. The intensity is going to rise. So we just look at we change this current and we look at the amplitude of the deuterium signal. It goes up. There is a line. Even if you have seen an NMR, it's unfortunate that we can't see NMRs. Right now. But if you have seen an NMR, you see that there will be a window where you have a line that goes up and down, in this direction across. And when you do the shimming, we will try to make it higher and higher and higher. And once we cannot anymore increase its amplitude, then we say, okay, we have reached the maximum shim we can possibly do. And that's how we shim.
Vinesh?
Yeah. Yes.
This is Professor Jagannathan.
Hello, sir. How are you? I didn't know that you were.
Nice talk. I was listening to you to brush up my memory of basics. Very nice. Very nice. Very nicely put it. And thanks for making my job a little easier tomorrow. So you introduced some of the concept of MRI. So I thought that would be very good for the audience, because they don't have any other lecture after this. They land up directly on MRI tomorrow.
Yeah.
So some of the concepts that you introduced are very good. I think that would be very useful to them. So that listening to your talk made me to also reorient my slides a little. So that I thought they would be knowing about the one-dimensional, two-dimensional. Now maybe little 1 or 2 slides I will add so that I can make it complete tomorrow.
Yeah, chemical shift is also covered little bit yesterday. Today morning, Dr. Bharadwaj from ISR Bhopal has done it. So he has. How are you, sir? How are you?
Fine. Fine. I moved to Chennai, you know, right now after the Ames.
Oh, I didn't. Last year. Last year.
And then I'm in Chennai, Chettinad Hospital and Ramchandra Hospital and also IIT. So.
Okay, good. Yeah. So Subbu sir, you met him.
A meeting was a problem because of the COVID, but otherwise we are in direct contact. Yes.
Great. Very nice. Is there any further questions?
I think no more questions in the chat box. Then you can switch on your mic and ask questions to Dr. Vinesh. If anybody wants to discuss about anything related to instrumentation and the theory, please.
Sir, may I get 1 minute for some announcement?
Yeah, sure.
Yeah, right now?
Yeah, okay.
Okay. So, dear participants, I will send you the Google Meet link for tomorrow's program this evening. So you can use that for joining. And only registration will not, you will get participation certificate only if you attend all the talks. That is very important. Okay. Yeah, thank you.
Okay, then I think no more questions from the participants. So,
yeah, if you have any other questions, please write to us or even talk. Give us even from morning's lecture. Also, anytime, any lectures. You have any questions? You think about any questions? Then please let us know. We'll be happy to answer.
Because today's lecture, both lectures, it's a package of NMR, especially proton NMR, the fundamental theories and also instrumentation.
Yeah.
So I think from the bio sketch of Dr. Vinesh, we know that he is a promising scientist and a good researcher. And from the talk, I can say that he is an excellent teacher also. So I think on behalf of all the participants and the MRSK team, even though he is the president of MRSK, just for formality, I would like to express my thanks to Dr. Vinesh for the wonderful presentation. Thank you, Dr. Vinesh. Thank you.
Thank you, sir.
You are a wonderful teacher.
Thank you. Omar has asked something. Omar Hisham, he said, most NMRs have temperature gradient option. Could you give us an idea about pressure variation NMR? Oh, a pressure variation NMR is not possible directly from an NMR machine, but you can have certain NMR tubes.
I am specialist in variable high pressure NMR.
Yeah,
I was Professor Akasaka. He developed the variable high pressure NMR of proteins.
Oh, great.
And temperature and the pressure are doing differently. They're acting. We are not giving any, when we change the temperature, we are, for example, when we increase the temperature, we are giving thermal energy into the system. But when we apply pressure, we need special cells for withstanding high pressure up to 3,000 bars, something like that. Experimental setup will be very different. But we are modulating or we are shifting the equilibrium, the conformational equilibrium in the molecule.
Yes.
So that is what we are doing.
Yeah. So any structural or conformational especially protein. Like Dr. Sunil is also working on the same. Was working on the same thing. So any conformational preference is for that particular temperature and pressure. So if you want to change the equilibrium, you either change the pressure. You can also change the pH also. Either change the pressure, you can change the temperature, pH. So then you perturb the system. You perturb the system, and then look at how it comes back to the new equilibrium. How it turns to the new equilibrium. So that is one applications. Now, how to apply pressure gradient? I think, like Sunil sir has said, we need to have a very specific apparatus to do it. Especially if an NMR tube and all, it has to withstand this high pressure. Withstand this high
so
pressure.
We use
so
ceramic tubes for
high
pressure.
So it has to withstand this high pressure tubes. These are not very these are very costly tubes that is there to do it, and it has to be also done very carefully because it can easily break also.
Yeah, it can break the probe.
That is
if it happens inside the spectrometer.
Yeah, many times it do happen, but not. I mean, even without any high pressure and all, it breaks. Then you have to clean it and things like that. Solid state or liquid, which one is the best one? Is there any difference in their sensitivity? So, okay, Anju, solid state and liquid NMR are two different things. I mean, it's NMR is obviously the same, but solid state. We generally don't look at proton NMR. We look at carbon-13. The reason being, as I was mentioning, I was mentioning that the dipole-dipole interaction is really huge for the proton because it is related to the gyromagnetic ratio, and the proton gyromagnetic ratio is the highest. So what we see in solid state is that the line width that you come to know in solution NMR is not what we have in solid state. Solid state is the line widths are much bigger. That is specifically, as like Bharat said, the isotropic tumbling that is there in solution NMR is not there in solid state. Solid state is basically frozen, right? So all the molecules see each other, okay, and therefore their energies can be easily dissipated, and therefore the relaxation rates are unfavorable for NMR. So what we do in solid state NMR is to mimic the solution state by spinning. And reducing the line width. Okay, so I would say solid state NMR and liquid state NMR. Liquid state NMR is easier to do, is easier to interpret. Solid state NMR is slightly more difficult to do and also quite difficult to interpret also because of the line widths problem. How is decoupling done in NMR? Asha asks. Now, decoupling is, see, what is coupling? Coupling is that the energy of one spin depends on the energy state of the other spin. Okay, so it's like husband and wife. If something happens to the husband, the wife is affected. Something happens to the wife, the husband is affected. If they have proper, that they have love for each other. So here, this is the same case. The energy state of one spin is affected by the energy state of the other. Now that is why they get split into two. Now why there is splitting? For example, if one spin gets split, if there is a coupling partner to another spin, it gets split into two because the second spin, and I'm talking about spin half. Okay, spin half, because there are two spin half states, plus half and minus half, for the coupled partner. So I'm looking at first spin, but it is coupled to the second spin because, and the second spin has two spin halves, right? And then plus half state and minus half state. Therefore, if the first spin is coupled to the plus half state, they will have a different frequency. If the first spin is coupled to the second, the minus half state, they will have a different frequency. The change in frequency is very small, and that is why there is a small coupling constant, J. Okay. Now, how do we get rid of this coupling? Now, how do we get rid of the coupling is to divorce. Now, you create a system where the husband doesn't see what the wife is doing and wife doesn't see what the husband is doing. Okay, so what we or another way, what you have to do is that we interconvert the alpha and the beta, the plus half and minus half state of the second spins. We keep interconverting. That means plus half goes to minus half comes to plus half. You keep interconverting. So the first pin doesn't know whom it is coupled to, whether it is a plus half state or the minus half state. And then it is so confused that it will come as single line. So it is not only coupled to the plus half, at different point it is coupled to the minus half also. So it comes in the middle, which is the decoupled state. Okay, so what we do in coupling is to do a 180. Very simply put, we put a 180 degree pulse on the coupled partner. So if let's say if you are looking at carbon-13 and proton, I told you they in this lecture they goes through two different channels, proton and carbon-13. So I am observing carbon-13 and I want to decouple proton. So what I do, I put 180 degrees. When I am observing the carbon, I put 180 degrees on the proton channel. Okay, I keep putting 180 degrees on the proton channel, and therefore this carbon doesn't see the spin state of the proton it is attached to, whether it is in the plus half state or minus half, because it is getting, each time it is getting interconverted, plus half, minus half, plus half, minus half. Okay, I think that is all. If there are any further questions, I'll be around, so you can ask anytime tomorrow also, if you find any new questions. Thank you, sir. I think that is it.
Thank you, Nmr sir, for the wonderful presentation and discussion. Thank you very much.
So, shall we conclude now?
Okay. Any comments?
Yeah, I think that is it. Tomorrow at 10 o'clock, right?
Yeah. And the Google Meet link will be open at 9:45.
Okay.
9:45.
Yeah.
Okay, good.
Okay, thank you.
Thank you, sir. Thank you, everyone, for coming, and hopefully you had a good session and learned something new. And hopefully you all turn up for tomorrow. There are very good sessions tomorrow as well. Jagannath sir is going to talk tomorrow, right?
Yeah.
Okay, good. So sir will be talking tomorrow, and it will be very good that you guys listen to her. He has been, I don't know, 40-50 years in MRI.
Almost 40 years.
Yeah, so he probably started when I was born or something like that. So I request all of you to come and listen to his lectures. Thank you, sir, and thank you, everyone. Thank you, Sunny sir. Thank you, Sunil sir.
See you tomorrow. Thank you.
See you tomorrow.
See you tomorrow.